All set? Yes. Okay. So the next lesson we're going to look at now is circuits. Can you write this down? Are you ready, Cookie?
Yes.
Yeah. Simple circuits. Right, so what exactly is an electric circuit? Who knows or who can explain what it is? Does anyone? I'm sure some of you have heard of a circuit before.
Wait.
Path, yeah. Yes, so there's definitely a path. Something special about the path though. Do we know? It can't just be any path.
It should be closed.
Should be closed, yeah. What does that mean to say it's closed?
That means the current can flow all these.
Yeah, but what does closed mean? You're right, it needs to be closed for the current to flow. But what exactly does closed mean? Like if I say close the door, you know what that means. If I say a circuit is closed, what does that mean? Do you know?
No existence.
No existence? No, it definitely exists.
No exit.
No exit?
No gap.
No gaps. It's getting closer. Yeah. But in fact, even that's not true. We'll see later. It's something else.
We should complete it.
Yeah, what does complete mean?
No energy loss.
Oh no. Now we're moving away. No, so it's like you understand. I think you all understand what it is, but it's hard to explain, isn't it? We have this idea that there should be a loop. It was really the key idea that there isn't really a. You were all very close to the idea. You said there's no exit. Yeah, there's no start and there's no exit. It's just a continuous. And when you said no gap, you all had the right idea that it's a continuous loop with no start or end. That's not broken or discontinuous or anything like that. So, I would say an electric circuit is a path in which electrons flow from a voltage or a source. The path is closed, and the point where the electrons enter the circuit is called the source, and the point where they leave is called the return or the ground. The exit point is called the return because the electrons always end back there. Now there's a lot here to write, and you don't need to write it all. So what would you need for an exam? So if an exam question was what is a circuit, you could say an electric circuit is a path in which electrons from a voltage or current flow, and most importantly, you need to say it's in a closed path. I mean, that's absolutely so important. So the first two sentences are enough for your exam, and if you like to write them down. First two.
You just say it's a closed path.
You want to make one sentence, because why two when you can have one? Yes, okay, that's fine. Got that? Continue. Bruce, you only need the first two sentences. Where are you? I talked to Connell about your active listening. Talked to Dennis about your active listening. So I'm disappointed. I gave him 4 great physics topics and he said, no. No, so I gave him a different topic, which was not a physics topic. And I thought these topics were great, but the problem was you have to do the active listening with the business students, and they don't like physics. Let's pick something else. So the 4 topics I was going to do, and I asked Dennis to pick one, and he picked none of them. I was wondering which one you would pick. So the first one I said is, the first active listening topic was how the universe will end. The first one. Huh? Yeah. The second one is time travel, a how-to guide. These are our real topics. The third topic I gave him was quantum mechanics versus general relativity. And the fourth one was also boring, the future of clean energy. And he picked none of them.
Oh, what are you?
Business students. Yeah. He said he thought the students would find that boring because you've done a lot of green energy in the AP class. It's true? No? Okay, right, whatever. Alright, so next now, let's have a picture of a circuit. So here's an example of a circuit. You need the source, you need the conductors, you need what's called the load. The load is like the resistor here. And you need the switch. And so this is a very simple circuit here. I think the word that you might not know is this one here called the load. In this circuit it's the light bulb. This is called the source. And this is the control. So can you draw this very roughly? And when you draw it, I want you to label load, source, control. Load, like a video game, load. Source, like book source, reference. And control.
Battery
is the source, yeah. Ah, now that's beautiful. Look at that light bulb. Oh, wonderful. Where's your picture? No picture? What the heck is that? Oh, no pictures, just words. Oh, okay.
So who will give us the lecture?
Don't worry, I'm giving you the lecture, in case you were worried. And it's not about physics.
No,
I'm not saying anything. I'm not saying anything. It'll ruin the surprise. You'll find out in the EAP. I think Dennis said he might tell you this week or next week. So he'll give you the sources. Yeah. I'll leave you guessing. Make it exciting. Okay, did you draw that? Yep. So next. Of course we can't draw such beautiful pictures all the time. That's a waste of time. We need ways of drawing these simply. And clearly. So we have these special symbols we can use. And these are quite common. I should say though, sometimes different countries use different symbols. I'm just showing the symbols we use here. But they can be different, like in the US or so forth. So, this symbol represents a switch. This one represents a cell. This one represents a battery. This one is a lamp. A light source, a lamp, a light. This is for a voltmeter, an ammeter. This is a resistor. It could actually be any resistor. So this could be like a computer, a TV, the resistor I showed you in my box, any resistor. And this is called a variable resistor. A variable resistor means you can change the resistance on it. There's like some kind of control on it. There is another name for a variable resistor. I wonder if anyone knows it. If their physics teacher has used it before in high school. Very good, rheostat. So, I need you to draw this table and write the names.
What's the difference there and there?
I'll explain that in another slide, yeah. Oh, Bruce, I prefer when you draw.
Kind of thing.
You can't see it. Alright. Alright. Okay, did you draw that? So the picture I showed you a moment ago, let's represent that in a circuit diagram. So in the last picture you had a battery. Yeah? What else did you have? You had a switch and a lamp. And that's how you would represent it as a circuit. So you can see it's very convenient to use these symbols. Continue? Yep. So, we can put connections together two ways, in series and in parallel. So, here's the difference. When we have the resistors, for example, together like this, we say they are in series. But when we split the conductor and have them running like this, we say they're in parallel, like in maths, parallel lines. So I need you to draw both of these. Now you can see that when I got this picture off the internet, this was an American website because they didn't use the same symbol for lamp. They used this symbol for lamp. Might change that. I saw on the news this morning that a maths teacher in America accidentally fired a gun in class. Accidentally. He was showing the students how to be safe with a gun. He accidentally fired it on the ceiling. A maths teacher, yes. Yes. So I'm just picturing, it's like, okay students, you have to be very safe with this because because you know the new idea they have in America, in Florida, is that to try and prevent school shootings, that they will give some of the teachers guns. Yeah, I wouldn't trust some teachers with a computer. So, a gun is a bit different. Okay, do you have this? Yep. So, as series and parallel, now a bit of English, because you were asking what's the difference between a battery and a cell. So, when we have one battery, we don't actually call it a battery. We call it a cell. And we have two or more cells, we call it a battery. So, if I have a 3-volt cell, that's right, you can say that, I have a 3-volt cell. If I have two 3-volt cells, therefore I have one battery. Is that right or wrong? That's right. Because I said two or more cells make a battery. I have three 3-volt cells, therefore I have one battery. That's still right. 3 cells also make a battery. I have 2 connected batteries. Right or wrong? It's wrong. Yeah, because you have one battery. Because it's a bit like yeah, if you have 2 together, then it's 1. The problem is, I'll explain what the problem is in a moment. If I have a 3-volt cell, therefore I have one battery, right or wrong? That's wrong. So I'm simplifying the English, but the rule is basically one is a cell, and more than one cell, we call it a battery. Now it gets a little bit confusing because in English, like day-to-day life, we call this a battery. And you might say, well, shouldn't I call this a cell, because I only have one of it? And what's actually happening is, you can't see this, but if you could open this, there actually is maybe 3 or 4 cells in it. Now if you think really hard about your laptop, maybe when you were buying your laptop and you saw where it said the specifications, you might remember that it said the battery is a 6-cell battery or a 9-cell battery. Because actually this really is, this is probably like a 4-cell battery. So I call it a battery because there's actually 4 cells in it. I think it's normal for a laptop battery to be a 6-cell battery, so there's 6 cells inside of it. Yeah. So I think this is why it's confusing, because we think of this as 1, but actually we should really think of this as 4. Laptop maybe a 6. Yeah. Does anybody ever notice that when they were buying their laptop? No, only I noticed that. Well, the next time you buy a laptop, if you have a look at the battery, it should say the size of it. Yeah.
But it has 6 cells and it has 3 batteries.
No, we still say it's 1 battery. We just say it's a 6-cell battery, but it's still 1 battery.
So when do we have 2 batteries?
Never. Even if I put 2 of these together, I still should say 1 battery, but maybe it's now 12 cells. The problem is, in English, battery means like we talk about a battery of an army. It means like lots of units. So it means like a group of things. So when I say a battery of cells, I mean like a group of cells. So I can't really say 2 batteries, because I only have 1 group of cells. Yeah. I suppose I could say 2 batteries if they were separated. I had 6 cells here and 6 cells here. But when I put them together and I have 12 cells, I say that's 1 battery. So anyway, the simple thing is, 1 is a cell, and more than 1 is a battery. That's all. Okay. So let's have a look now. Some basic rules. So let's first look at current when it's in series. So what I mean is, you have something like this. Ammeter. So maybe you measure the current here and the current here, for example. So if they're in series, current is a constant. So that means these 2 should be equal then. I1 equals I2. Okay, so that's the first rule. So you should write these rules down. So series, current is constant.
I mean, I1 equal I2 equals total I.
Equals total I as well, yeah. Okay. Oh, I forgot to say something actually. I just remembered I forgot to say something in the diagram here. I forgot to tell you this. The longer side is the positive side and the smaller side is the negative one. And the current flows that way around. Positive to negative.
I mean electrons.
The electrons then are flowing this way around. Yeah. Okay. Back to my slide. Next one is resistance is additive. So, if I look at resistance now, this one is R1 and this one here is R2. If I want to think about what the total is, it's simply R1 plus R2. That's equal to the total. So the second rule is that resistance adds, R1 plus R2 is the total R. Yeah. Continue. Next one. So the next one is voltage. So let's imagine I measure the voltage here V1 and I measure the voltage here V2. These will be different. And if I was to measure the total voltage for the whole series, then the total voltage would equal, you could probably guess, V1 plus V2. So voltage is different and it adds. So V1 doesn't equal V2 and the total voltage is V1 plus V2. Okay, and we continue. I just realised coming up is a typo, I think. Right, next now is the battery. Plus with a minus causes an increase. Actually, that's not a typo, that's fine. Goodness sake. So what I mean by that is, if you're making a battery and you put the cells together, if you put the cells this way around, plus minus, plus minus, plus minus, so this is the right way to do it. If this was a 1.5 volt, and this is a 1.5 volt, and this is a 1.5 volt, well, they add together. It's like you've made a battery, 3-cell battery, and it would say 4.5 volts. So actually my phone is 4.5 volts and I think it's 3 or 4 cells. So it's probably, now that I think about it, a 3-cell battery, each cell 1.5 volts, total is 4.5. So plus with a minus adds. However, if you put one of them in backwards, so for example, if you do something like this, let's say this guy is a 10 volt and you put it the wrong way with a 2 volt. In fact, what you've just made is an 8 volt battery. So if you put,
The current flow.
Yeah, its flow is, but you have reduced it by putting it in backwards.
What's the direction?
So the 10 volt will win, so the current will still flow to the left because it dominates the 2, but the 2 has the effect of reducing if it's in backwards. So this is why you shouldn't put your batteries in your toys backwards.
But they don't work if we put them backwards.
Yeah, because what's going to happen is, for example, if you have 2 AAs and you put them in backwards, and this is a 1.5 and this is a 1.5, then you've just made a 0. So you get nothing then. Yeah. Okay, so if you can write that rule down. You notice that your Tamagotchi stopped working if you put the batteries in backwards. Does anyone know Tamagotchi? No? Too old? I'm too old. You know Tamagotchi? Good man.
With the pet,
No.
feeding your pet.
The virtual pet.
They always die.
And they obviously do. Yeah. No. Don't know Tamagotchi. Missed out. Very big childhood toy. Tamagotchi and Furbies. You know Furbies?
Yeah.
Yeah, exactly, yeah. So you know Furbies. It looks like they creep you out. Yes. Tamagotchi's great, huh? Continuing. Well, what's popular toy now for kids? Legos don't need batteries. Okay, iPad, yeah. Apple iPad, yeah. Right. So now, parallel. So if the current is parallel, then they're different and they add. So what I mean is, if you have a current here, I1, flowing this way, you have a current here, I2, flowing this way, and then they meet, these will be different, but the currents, when they meet, they add together. So, current is different and adds. Okay, you got that one? Yep. Next is voltage, I think. Or maybe I'll do resistance next. Yeah, so resistance, we say the reciprocal adds. So what the heck does that mean? So if you have two resistors, one here, this is R1, this is R2, and you want to know what is the total, then to calculate the total you need to use this formula, which maybe some of you have seen before. So the reciprocals add, which is like this. Have you seen this before in middle school or something, this formula? Yeah? Maybe? Anyways, next one is voltage. Does anyone know or think they know what might happen with voltage? Yeah, the voltage is constant, and I'll just draw that. So here, I didn't actually say this in my slide, but this voltage will be the same as this voltage, and not only that, but that's also the same as the total voltage if I put a big voltmeter around everything. So voltage is constant everywhere when in parallel. And the last one, the battery. So if you put the batteries, or if you put the cells in parallel to make a battery, so for example, if you have one cell here, and you have one cell here, something like this, to make a battery, how do the voltages combine? We'll study this later. Complicated. A little complicated. Later lesson. Okay, do we have these rules? Yeah, continue? So now, most importantly is, let's use these rules for an example. So here is a circuit. This is resistors 1, 2, 3 and 4, and I kept it easy. I said their resistances are 1 ohm, 2 ohms, 3 ohms and 4 ohms. And in the middle is a cell, and the cell is 5 volts. Let's draw this. So, 1, 2, 3 and 4, and in the middle is a 5 volts. 1 ohms, 2 ohms, 3 ohms and 4 ohms. And it's connected like this with this one in the middle. And my question is, find the current. And find the current everywhere. So what's the current here, 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 and here? Yeah, we have to do something with the resistance first. Resistor 1 and resistor 2, are they in series or parallel? 1 and 2 here. So what formula could I use here? 1 plus 2, 3. So are you happy that I can replace these with just a 3? Like that? Yeah? Okay. And this guy is still a 5. Okay, now, what about the 3 and the 4 on the left here? I could replace them with 7. So now my circuit looks a bit like this. Is that okay so far? So I've gone from here to here. Okay, continue in my pictures. Right, well what should I do next? Because this looks a bit hard. Like, what the heck is this? Is this a series? Is this a parallel? It looks quite weird. Yeah. I should grab this cell and move it. You're happy that I could move it and not change it. Like, for example, if I was to do this, that's tray, just, you know. The wires are flexible, aren't they? I can move things around as long as I don't disconnect them. So what I'll do is, I'll take this and just carry it over so it's on the other side, so it looks a bit clearer. Alright, so let's see where we're at now. So now I have my 5 here on the outside, and then here is the 7, and then here is the 3. Now that looks ugly, so let me just straighten it up. So I'll just put my 3 like this, and my 7 like this, and my 5 here. And you realise, oh, that's a lot clearer now, because we can see what the relationship was between the 3 and the 7. Were they in series or were they in parallel? They were in parallel. So how did the resistance combine here? The 1 over, isn't it? So 1 over 3 plus 1 over 7, that's a 21, that's a 9 over 21, isn't it? Yes, 10 over 21, thank you. So the OR is 2.1 ohms. So now I've simplified it even more. Wonderful. So now can I get the current here? I can by using VIR. So what does the I equal? That will be V over OR, which is 5 over 2.1. What is that, please? Yep. If we could use a calculator instead of sound effects, that would be wonderful. Be wonderful. 2.38. Okay, 2.38 amps. Now we have to go backwards now. So if I go back to this picture, can you see that that means here is 2.38, here is 2.38, and so on, and here is 2.38, and here is 2.38. So in red I have 2.38 amps. But is it right to say that these are 2.38? No. But what I can say is that they add together to make 2.38. What do I know here? I know the voltage, yeah, because this is a 5. So it means here is a 5. And because they're in parallel, each of these is a 5. So again, by using this formula, I can say I is 5 over 3 and 5 over 7. So I guess I didn't really need to go to this picture, because I could have gotten it from this picture. I could have said, here the I1 is 5 over 3, and here the I2 is 7 over, no sorry, 5 over 7. Can you tell me what those are? 5 over 3 and 5 over 7?
1.6. 1.7.
2 decimal places. 1.7
1.67.
and 1.67?
Yeah. No.
Okay, so
1.67.
thank you. 5 over 7.
0.78.
79 then. Yeah? 2 decimal places? 5 over 7?
No, 0.71.
Okay, thank you. Now, that makes perfect sense, because if I add these two currents together, what do I get? 2.38. Okay, so let's go back to this picture. Where are those currents? This one here is 2.38, and this one here is the 0.71 and 1.67. Okay, I need to try and get back to my picture here. So if I go all the way back here, this one here is this one is the 2 point, in blue is the 2.38, and then this splits, and this one was the 7 on this side, and this one here was the 3 on the other side. The one with the 7 was the 0.71 amps, and this one here is the 1.67 amps. So on this side of the circuit we have 1.67 amps, on this side we have 0.71 amps, and in the middle of the circuit we'll have 2.38 amps. Okay? So, you know, the lesson is called simple circuits, not because it's easy, but because the diagram looks simple. It's not too complicated. But you actually have a lot of thinking to do here to get to the answer. But we are just using the rules. We just have to visualize the circuit. Is this okay? It's not too bad, I hope. I think probably that was the only example because it covers everything. So we have some questions to do there. So we have about 10 minutes left since we have no break. So can you try your best to do some circuits now? Can I close this?